Hi, and welcome everybody to this webinar on how to build reliability into your product. This is a webinar by RSQ-Labs, a division of the Sofeast Group. And I am joined by my colleague, Andrew Amirnovin. So I'm not going to read everything, but basically both of us have accumulated a lot of experience in new product development. Andrew more on the product integrity, product reliability, durability side at companies like Nokia, AT&T, LG, GoPro, and others. So he's got a lot of experience on electromechanical products, and myself more on the manufacturing quality side. Okay, so we're going to cover 4 topics today, right? Because building reliability into your product really involves, let's say, 4 different topics. Okay, the design reliability, the testing for reliability, manufacturing controls, and then during manufacturing, once manufacturing is going on, ongoing testing. Okay, so we're going to cover these 4 topics. And first, we have a few slides on what is quality and why is it so important. We're going to go a little bit fast on that, but let's go through it. Andrew, this is a definition that you like from the American Society for Quality, right? Can you unpack it a little bit? What exactly is reliability?
Well, hi Renaud, and good to be here. And thanks for the nice intro. Well, reliability is really the probability of product performing its intended function under stated conditions without failure for a given period of time. Of course, this is ASQ's definition. What it really entails is that if you are making a product and it's supposed to work for a year, then you want it to function for a year without any kind of problem, and that would mean a reliable product.
Right. So if I put out a car and I give a warranty for 50,000 miles, I want to make sure as a manufacturer that if it's used in normal road conditions, plus a little bit of abuse, maybe from time to time, let's say 95% of the time is going to go through these 50,000 miles without like a major failure, like with people having to go back to the garage to get it fixed, right? Is that a good?
Exactly.
Okay, all right. Okay, so with that out of the way, a lot of people confuse, okay, design issues and manufacturing issues and like reliability and quality. So is it fair to say that reliability is really built in the product at the design stage, while product quality really comes from good manufacturing processes?
Yeah, that's correct. Basically, reliability is part of the design, meaning that if the design is not reliable, then basically the whole product is not reliable, regardless of manufacturing. However, when it comes to manufacturing, if there are issues that relates to manufacturing only, then we're talking about manufacturing quality issues. We're not talking about necessarily a design issue.
Right. Of course, it's a bit more complicated than that, right?
Yeah,
What are
absolutely.
manufacturing issues still creep in the product and make it poorly reliable? Maybe, especially
Right,
1,
right.
2, 3 months after delivery, the early failures. A lot of them are due to
Yeah,
manufacturing quality, right? But this is
correct.
a nice way of sort of looking at it, right? So why is it important to pay more attention to quality pre-launch to save cost post-launch, right? So there's a direct impact on lower cost once the product is on the market.
Right.
So why is that?
Well, I mean, if you are trying to make a reliable product, then you wouldn't have all these issues that we have in the red section. For example, you'll end up having at the least additional inspection issues, trying to figure out how to fix these issues. And then, of course, rework and repair problems, maybe even massive returns and product recalls that needs to be dealt with. Lots of sales and revenue impact. Of course, tarnished brand and marketing image that would definitely hurt customer complaints and investigations, high warranty costs. We're talking perhaps even need for excess inventory to cover all those losses and issues. And then at the end of the day, we're talking legal issues, litigations, and lawyer fees. All of these and every one of these are considered to be some sort of cost, and you add them up, it'll be a huge cost.
Right. So good design for reliability and good testing to catch the issues and so on and so forth will prevent most of these costs, right? So that's really why we're doing this webinar. And the higher the volume of production and sale of the product, or the higher the price of the product, the more this is important, right?
Yep,
so
that's right.
Let's look just very quickly at two very dramatic examples, okay, of catastrophic reliability failures that cost billions of dollars. So one was the Galaxy Note from Samsung a few years ago. And this was really a reliability issue, right? It was due to the design of the batteries and the packing around the batteries, right?
Yeah, it's true. I mean, imagine that just one battery caused so much issues for a huge company like Samsung. If any other company had this problem, they'd be out of business for sure.
Right. Maybe another, like Apple or Google might have survived also, but this is not for smaller companies, right?
Correct.
Yeah, another one was the 737 MAX that has been grounded for years and years. But basically, this also is a reliability issue. Lack of redundancy, they only relied on one angle of attack sensor, not both of them. They did not tell the users, the pilots, about the MCAS software. They did not test how the pilots would react. The regulators did not, were not even aware of it. I mean, all of this was really during the design phase. All these catastrophic decisions, right? So again, billions and billions and billions suffered by Boeing and their supply chain. So let's go into the beef of this presentation. Okay, we said 4 topics, right? How to build reliability to the product, and really why 4 topics. What is the logic here, right? So you have the NPI phase before manufacturing, right? The product design, development, and so on, and then it gets transferred into manufacturing, right? So these are 2 large topics, let's say, and we're going to cover under the NPI some topics on the design of the product and on the testing. Okay, testing, a lot of the testing is done during design and development to detect the design deficiencies, if there are any, and address them. And then later on in the design and development is more to sort of confirm that, okay, there's nothing major, right? And then you go into manufacturing control, very, very important, because this will definitely impact product quality and also reliability. And then the ongoing sort of tests during manufacturing. So we're going to cover these four topics. And first, design for reliability. Okay, design engineers need to be aware of certain guidelines, some really important considerations to keep in mind. So Andrew, what is DFR?
Well, DFR stands for Design for Reliability, and really what it means is that you want to take out any kind of risks related to reliability. Some of the risk analysis tools such as FMEA, which stands for Failure Mode and Effect Analysis, and then of course FTA, Fault Tree Analysis, can be used to do some risk analysis ahead of time. But then at the end of the day, next slide will show you that there are a lot of other tasks that need to be done in conjunction with the design that will actually make your product more reliable. And these are some of the tasks that we're talking about. For example, understanding how your product will be used is very important so that you can design it more reliable towards that goal. Risk analysis, we talked about. Testing at various stages of the development and manufacturing to make sure that your product specification and reliability goals are being met. And of course, making the product more robust. And we're talking about robust in terms of better design, better components that are used, and so forth, and materials, and making the failure diagnostics easy. This helps a lot when you're doing the design, so you can, before you even get to the manufacturing, you get to see what is not failing and what is failing that needs to be fixed. And of course, planning for some maintenance and repair if needed. And then, of course, possibility to replace failed components when you got returns coming in. So all of these are just, in short, some of the tasks, but there are probably a lot more best-in-class activities that needs to be done related to design for reliability.
Right. And this is an example of an FMEA, right? So it basically is a risk analysis at the design stage on the product. And then you divide it first by maybe by function of the product or by module, or right, you have some kind of logic that you follow. And then yeah, you sometimes it's nice to break it down also per requirement. And then okay, how can it fail, right? Or per function, simply. Maybe this is not needed, but per function. And then what is the impact and the severity? What can it be prevented? Can it be controlled? And can it be detected? So the likelihood of occurrence and then the likelihood of detection. You multiply all these, you have a score. If it's a very high score, then you use that to prioritize your risk treatment plan, right? To actually act on them. And then you also mentioned the FTA, fault tree analysis. So this one is more top down. Okay, what can happen? Like, what are the big issues? Like, okay, it's gonna, like, this phone is gonna catch fire or explode, right? Or okay, so what can lead to this, right? So you try to break it down in your analysis, and you try to see, okay, in this case, well, this might be an issue, might lead to ignition, and then the fuel leak might come from this, or this. Okay, how can we reduce the probability of these situations that will lead to the hazardous situation here, where we have all three, right? Okay. Testing now. Okay, so this was the design and the analysis and improving the product design. Now, when we talk about reliability, there's all kinds of testing that we can go through. Do you want to just go along? So basically, this is from the very first phase of the product design and development, all the way to going to the feasibility study, proof of concept prototype, the prototypes to EVT, and then design validation testing, production validation testing, and then going into mass production and up, right? And at each of these phases, there's different types of tests that typically make sense. Do you want to run through them quickly so people understand all these acronyms?
Absolutely. I'm glad you mentioned that there are these different phases, in at least in our process, we have, for example, phase 1, 2, and 3, and so on, specification phase, feasibility phase, prototyping, tooling, and so forth. At the beginning, I think on the phase 1 and 2, the proof of concept, really the product is not durable enough to do any kind of reliability or testing, except that you probably want to do functional testing, of course. You want to see if design is coming along okay. But once you get into Proto 1 and 2 and so on, the prototype is complete, you probably want to do a really good major design review to make sure that everything is meeting the design goals. That's right. And then once you move from Proto to EVT1, which is engineering validation, that's when you're trying to determine how fast we can find major issues so we can fix it right away. I think for certain projects that are big projects, heavy projects, and multiple components, I think HALT would serve well. HALT stands for highly accelerated life test, and it really is very effective if you're running, let's say, multiple types of stresses all at the same time. You're running temperature, humidity, and vibration at the same time. Maybe you even changing the voltage and current, and you're trying to see under these massive stresses what's going to happen for the product. In some cases, you can also use HALT test as a test of failure to see the limits of the product in terms of reliability. But then as you move towards design validation, DVT 1, 2, at that time, the product is more durable, more, let's say, reliable, but you just want to make sure in terms of time, how long it's going to last before it starts breaking or having issues. That's when you do accelerated life test, which typically is more of a slightly higher stresses than what would be in a user environment. Then, of course, once you are close to production and your ALT has already passed, you wanted to run some life testing. And life testing will be more of a realistic product testing over long period of time, sometimes 500 hours or 1,000 hours, depending on the type of the product and the use case. And this would really, really help understand whether the product does have any kind of a infant mortality, and the beginning of the bathtub curve. And then, of course, once you go to production with a little bit of high confidence, it would be good to have a process, mass production, exactly. It will be good to have a process called HAS, that's highly accelerated stress screen. This is where you are actually running screening on the production to ensure that the product still is meeting the minimum reliability requirements. And then what happens in the HAS, which is a little bit different than the ORT, ongoing reliability testing, usually you run the HAS right at the beginning of the production, because you really want to catch all those production related mainly issues. But once the HAS passes and now you're past, let's say, the 30-day period in production, and then your volumes are increasing, then it would be really nice to have an ORT, ongoing reliability system, in place, where it would, with small size samples, would basically screen out design related issues, performance related issues, specification related issues, things that are critical to the reliability of the product. And then if there are failures, then you need to stop the production if necessary, and you need to do a full reliability test to ensure if the product changed, something changed, component changed, or something in the manufacturing change that needs to be fixed.
Right. And just to reassure everybody, to build reliability into a product, usually it doesn't involve all these different types of tests, right? This is for maybe products to be made in large quantity, et cetera, right? But in many projects, maybe it just involves some accelerated life tests, some life testing, and then very sort of light ongoing reliability tests, right?
Yes, that's exactly right. I'm glad you mentioned that. This does not necessarily apply for every product the same way, because it depends on the size of the product, type of the product. For example, medical product versus a consumer product, big difference.
Right. Yeah, some products come with failures can be disastrous. For some others, it's really not the case, right? And then, earlier we mentioned, how easy is it to fix, to replace components, to do maintenance, and so on. Well, this is a fun photo. This is a BMW. You need to bring it to the garage to do pretty much anything. Versus this is an old Toyota model where you have everything easy to access. This is really more, this is really a pleasure for people who like to do little fixes by themselves. Okay.
Yes.
Design for quality also very important, because as we mentioned, quality issues will impact reliability. If it prevents the product from actually functioning, that's a big problem. So it's usually done at the same time as design for manufacturing, design of assembly. Okay, I'm not going to go through this in much detail. I think a lot of people are already kind of familiar with that. Okay, preparing a checklist, knowing actually, okay, this product, for example, a camera, okay, how exactly is it going to be checked? What are the important tests to be done during production, at the end of production, and so on, so that everybody's on the same page, and really building sort of a standard also on the. So, for example, this kind of gap between two components that get assembled is kind of typical. Okay, so what is acceptable, what is not acceptable? And as much as possible, try to set a standard, right? So very often there is a way to set a standard. So for example, for gaps, this is something. And gaps, by the way, are not just causing aesthetic issues, can also lead to failures sometimes, right?
Yes.
Especially if it's supposed to be dust proof or waterproof and so on, right? So there are usually ways to test, and sometimes a custom gauge has to be developed and so on. But if you start to look at it from the angle of reliability of the product, okay, can a failure here on the quality side actually lead to a failure of the functions of the product? If yes, then it's very important to spend the time to do it right. And finally, DFM, we want to cover this, design for manufacturability, very, very important. If the product itself, the product design requires some manufacturing processes that are not very mature, not very common, the use of certain components that usually are not, assembled or treated in a certain way, etc., there's a high chance that things will go wrong because it's not the manufacturing itself is not mature, right? And we're talking about design for manufacturing, also for assembly, right? Anything that simplifies is good because it will reduce the opportunities for mistakes. This book here about DFMEA, it's a very popular textbook. It's got a lot of examples. This is just one simple example about cantilever snap fit. So when you assemble, why like put it together, then have to screw and so on and so forth, right? And then the screws over time can maybe get unscrewed slowly, or they might not be at the right torque, and then you can have a lot of issues. Now, if it can be simplified like this, it just snaps together, and that's it. And the operator actually hears the click. That's the best, right? When it actually makes sense. When it makes sense. Very simple work instructions and also simple assembly process. This is from IKEA. I guess most people would have recognized that. But this is something that we like to use as an example also for manufacturing, because if you can simplify and make some very simple work instructions, well, all the best, right? And this is part of manufacturing control. So manufacturing control is a very deep topic. Do you want to pick 2 or 3 of these topics, Andrew, and explain a little bit what we mean by manufacturing control?
Yeah, sure. I think that basically one of the most important thing in manufacturing control is control plan. You have to have a plan. You have to have a way of how to keep everything under control, and it's basically a process that says, we're going to be doing what during the process and how.
Actually,
And
yeah, control plan looks like this typically.
yes, this is an example. Exactly. Yeah. And it's very detailed. It tells you each process is, for example, process name, machine that is being used in that area, and then products and the process and materials, and maybe even there are some instructions and how you evaluate whether or not it's working, how many pieces you need to, for example, pick for inspection during the process. It's a very detailed process, and I think for any kind of a complicated manufacturing process, this is critical. And of course, during the assembly process, mistake proofing is critical. You have an assembler that comes to work that is not in a good mood, and then what if they start assembling the wrong way or different than the person after or before? So it's very important to have a process in place that it doesn't really, an operator couldn't really affect the reliability or quality of the process. And then, of course, all operators need to be trained ahead of time so they all know what they need to do. It's very important to have some automation or more automation if possible, and then create some jigs to keep the process more consistent. And of course, creating standard operating procedures so everyone in the assembly line know exactly how they're supposed to be, following the procedure that it's standard for everybody. Work instructions are critical. And then, of course, in an electronic type of manufacturing, EST control and having EST clothing for all the operators and all the tables being in EST control is very, very important. And then at the end of the day, all the KPIs from quality need to be monitored so that you can see how your manufacturing and how your production is actually running.
Right. And then we also mentioned testing during manufacturing. Yeah, we mentioned PVT, right? Production validation testing or pilot, which includes some pilot runs, qualifying the materials properly, of course, with incoming quality control, some specific tests on the PCBA, and then as you get the assembly done, first article inspection, then ongoing patrolling, sort of in-process quality control, and then outgoing, let's say batch by batch, and as we mentioned before, so in parallel, picking a few samples for ongoing reliability testing. All of this, there needs to be a plan and it needs to be done in a routine manner. All right. That's how you pick on variation. So we already covered this. This is an example of a control plan. When you go into production, there's a lot of issues that come up, right? And you need to prioritize them and go at them one by one, right? There's going to be quality issues, and there's also going to be, let's say, productivity, efficiency issues, right? But then if we just look at the quality reliability side, right, you need to prioritize, and typically these types of analysis where you arrange them by order of frequency. So you attack first the ones that amount to maybe 80% of the failures, and then over time that's how you have the most bang for your buck, let's say, in your remediation actions. Okay. The way you design the manufacturing process, and this is something we see all the time in Chinese factories, in Vietnamese factories, the way to design the manufacturing process is extremely important. So this is a nice little graph from this nice book where they show sort of a lot of the typical issues, right? So you have a lot of inventory. This is probably not one piece flow. So the operators kind of can forget, hey, did I do it on this one? Or oh, this one, maybe I did it twice. I'm not sure now, right? It's a bit of a mess in the layout. They keep working even if other processes are slow or are stopping, so it builds even more inventory. Sometimes need to be reworked. I mean, all of this is really an insult to manufacturing process quality, right? You really need to avoid this. Okay, how to test for reliability. A lot of the work in reliability engineering is actually putting together testing plans and arranging for testing, right? So sometimes this, I think, is in an IKEA store. They show, hey, here's the way we test with whatever 5,000 cycles. We press with this this shape here, and it's sort of the weight of an adult person. Okay, another kind of similar test on packaging is compression, right? If you're going to put a lot of carton in a container, there's going to be a lot of weight on it. Okay, let's test to make sure it actually can resist that sort of compression force, right? So these are just two simple examples, simple to understand. There's a lot of different equipment. I'm not going to go through all of these, but the most common reliability testing equipment and so the most common sort of the reliability tests are listed here. Now, one thing very, very important for people to understand is that some of these are very common. So for example, the product has buttons and you want to click on the button a certain number of times to see if the button after a while is going to stop really clicking or is really going to feel different, right? That's an example that makes sense across a very wide range of products. But then there's a lot of very product specific tests, right? Maybe you can tell us a couple of examples so people understand.
Yeah, absolutely. I think that, you've got sometimes very simple products that it's very easy to understand the use case. Someone is going to probably drop an iPhone, so it's very easy to understand that what can we do so that this iPhone glass doesn't break, for example, right? But in some cases, it's not so easy because it's a brand new product. For example, it's a brand new company, brand new product. It's cutting edge. Never ever, no one has ever used it before. The use case is actually not clear. And at the same time, when the use case is not clear, it's very difficult for designers or even reliability engineers to design a use case that can actually test this situation. This is where we get involved with the designers, we get involved with the product managers, and we try to understand the real user environment in terms of how the user itself will actually use the product, but also in what are the worst case environment that this product could be used. Could it be used in a very cold environment, very hot environment, very rough and rugged environment, for example? And for each one of these, we will have to create a specific custom reliability test case that would mitigate these issues, so that when you test during the development phase, you find these issues because you're basically trying to mimic and simulate the real life scenarios post-launch. And if you can do that during the development, then you'll get to find these issues that the designers can actually fix. And or, you know, if there's a component issue, then you find another supplier. If it's related to production, then you tune up your production. So basically finding these issues early in the development is critical because of the test cases that you develop, especially custom test cases. Then hopefully you will never see them in the field.
Right. This is another list of another way to show it, right? Very common test, but again, has to be customized to the product. For, again, let's say a car. Well, they will have a way to a special test station to open the door and slam the door 5,000 times, for example, to see if after 5,000 times, you know, the way it closes and the way it feels and so on.
Or the hinge drops.
Yeah, right. If it can basically withstand the stresses that can be reasonably forecast, right? And this is our last slide, but this is just to show an example when we do a custom test plan for a product. So this was for a Wi-Fi router, I believe, yes. And
yes.
So there's some very common tests like high temperature, low temperature, temperature shock. These are pretty common. Some of them are based on a standard that actually makes sense, can be applied on that product. So for example, temperature and humidity testing here, typical accelerated life testing, okay? But then, and some vibration testing also, there's an IEC standard, and okay, this is the method that makes sense for this product, and go ahead. And then in some cases, there's a custom protocol that makes sense specifically for that product. So that's what you were mentioning, right?
Yeah, exactly. And I think actually the ALT is, well, ALT, vibration, USB contact test, connected test, and life test, and button press. All of these are pretty much customized tests with respect to the use case of that product. For example, in the ALT, we need to understand, for example, what are the high temperature, low temperature, how many times, how many cycles we need to run this product that makes sense based on the use case and the warranty limit and so forth. So all of these need to be customized. If not, you're really not going to get the results that you're looking for. One important thing that I need to mention that a lot of people may misunderstand. So when you're using standards are for guideline only. That means that you can use the way the standard is directed to test, but those standards are very common for, let's say, generic, and they're used for all kinds of products, small or large. And maybe your product doesn't exactly fit into that. So you are welcome to change and modify the standard. So you can say, for example, per this standard, with the exception of this part, and instead of doing 1 cycle, let's do 20 cycles, for example.
Yeah, right. A lot of these military standards are still pretty common for reliability testing, but they're usually for pretty advanced, things that you might maybe shoot into space or things like that. Doesn't necessarily make sense for simple B2B or consumer electronic products or products without electronics. All right, so thanks a lot. This was a webinar again about how to build reliability into a product, and feel free to send us some questions, contact us if you need help or need some guidance on this topic. Thanks a lot, and see you in the next webinar.